Hello, um, welcome to microcontroller interfacing class. Today we are going to, in this video, I'm going to talk about the analog to digital converter, ADC. This chapter explores some of more real-world devices such as ADC and analog to digital converter. And you may have heard of this device before, especially if you want to connect your microcontroller with other devices and sensor and such. Okay. To describe an analog to digital converter ADC chip, we will study the 8-bit parallel ADC chip. If you look into our textbook, the Mazidi book, you can go to page 374 in the Mazidi book. Now, in the Mazidi book, the example used are the ADC 0804 and also some instruction on the ADC 0808 and also 0809. For our application in our lab, we are going to study on the ADC of 0808. Okay, so getting on to analog and digital converter. First of all, we're going to look into what is an ADC, the conversion process, accuracy, example of ADC applications. Okay, signal types. Okay, when talking about signal types, there's actually only two types of signal in any application. The signal either comes in analog signal or digital signal. So here we have the analog signal. Any continuous signal that's the times that are time varying variables of a signal is a representation of some other time varying quantities. That means you have a signal that changes due time. Those are called analog signal. For example, speedometer needle as the function of speed, radio volume as a function of knob movement when you change the volume of the radio. Okay, so those are what we call as analog signal. And then the second one is the digital signal. Consists of two states. Either it's in binary states, an on and an off. Computer can only perform processing on a digital signal. Okay, so how do you mesh those two signals between an analog and a digital signal? Okay, to use an analog signal in a digital world, you need the use of an analog to digital converter. So the use of an analog to digital converter, an analog and electronic integrated circuit which convert a signal. The term for ADC are an electronic integrated circuit which convert a signal from analog continuous to digital discrete form. Provide a link between the analog world of transducer and the digital world of signal processing and data handling. So here, the main thing that you need to hold is that ADC, analog digital converter, changes the signal from an analog or a continuous signal to a discrete signal or discrete form, so that your computer can understand the signal. Okay, so now looking through the ADC converter again, an electronic integrated circuit which convert a signal from analog to continuous, to digital discrete form. So here's an example of analog signal. Okay, so next, so this is example of discrete signal. So even though the signal have the same amplitude, the same wavelength, however, one is a continuous signal. That means the signal is changing due to time, and another one is a discrete signal. Also, the signal is changing due to time, but now we are able to pinpoint the location of the signal in each time. So that's the analogy difference between continuous and discrete. Continue on. Okay, ADC conversion process. So what's the process of analog to digital converter? The two main steps is for it to have one, sample and hold, and two, quantization and encoding. Okay, so for an analog to digital converter, when we have an analog signal, okay, the sample and hold, that means the conversion between holding a signal at a certain period of time is called sample and hold. That means we take the sample of an analog signal during the time of conversion and hold that signal at a certain amount of conversion to change it to a digital signal. Okay, so here we have a diagram showing a sample and hold. That means each time a signal is triggered, here it's represented by a switch. Each time the signal is triggered, is in the representation as a switch. Each time the signal is triggered by a switch, that means it will change the triggering time between low and high following the analog signal. And then the next step is quantizing and encoding. That means how do we quantify our signal value and we encode it so that we can know the binary that represent that value. Okay. ADC process, sampling and hold. So if we have a signal, a continuous signal like in this signal, okay, the signal will travel due to time, okay, and then we will sample the signal in a particular order of time, measuring an analog signal at uniform time interval. Here, as you can see underneath the table. So let's say we are sampling the signal every 1 millisecond. So every 1 millisecond we take the reading of where the signal lands on the y in the x scale. Okay, so we will plot in a 2 coordinate form the height of the signal and the t of the signal. So there, what we're doing now is we are using the method called sampling and hold to make a coordinate form of the signal. Okay, sampling and hold, measuring analog signal at uniform time interval, ideally twice as fast as what we are sampling. That means the ideal method of sampling is to sample it twice the time of what we are able to sample. That means if we are able to sample every 1 second, we do it every 0.5 millisecond. If we want to have a signal for every 2 milliseconds, we sample every 1 millisecond. So we have twice the data. Okay, so this is most of this for digital system. Let's go through it more. Okay, sample and hold. Okay. Measuring analog signal at uniform time interval. Again, every time interval we at uniform means we fix the value of time for sampling. Digital system work with discrete state, taking sample for each location. Reflect, sample and hold signal digital approximation. Okay. So by doing this, what we do is that we are now trying to map the signal in a 2D world. From an analog signal, we are going to map it. So what does the value, what is the value of the signal represented by the analog signal due to time versus time, something like that. So now we know that the changes of signal are following the changes of time, and when we do a uniform time interval plotting, we got our sample. So quantizing means separating the input signal into a discrete state with k increment. That means now we want to know our resolution. So here, if you look at the equation, k is equals to 2n. That means n is the number of bit of the ADC. So we will go through the number of bit later on. But here, what it means is that the number of bit representing the ADC are due to the power of 2 power of n. So it means that we are going to represent our signal in digital. Digital consists of 0 and 1. That's why we use 2 power of n. And then analog quantization, size. The size means we want to know how many bits does the resolution can able to support. So the quantization formula is the voltage, maximum voltage to minus the minimum voltage and divided with 2 power of n. So that's going to give us our resolution, or going to give us the ideal resolution to represent our signal. And encoding means to change those values into 0 and 1 so that our microprocessor can process that data. Okay, using original analog signal, we do quantization, encoding, and then we will get our sample. So what ADC does is that it changes the value of analog to the value of digital. Okay, using original analog signal, apply a 2-bit coding, so you will get, let's say our signal is going to have a resolution of k to power of 2. That means the whole signal is going to be represented by 2 bits. 0, 0 means the bottom line, 1, 1 means the highest, the Vmax. So this is V low and this is Vmax. So 0, 0 is V low and 1, 1 is going to be Vmax. So in between 0, 0 and 1, 1, you get the transient step of the signal. So this is what we call as step. 0, 0 to 0, 1 is one step, 0, 1 to 1, 0 is another step, and 1, 0 to 1, 1 is another step. So this is what we call as signal step. And then going to the quantization and coding using original signal with 2-bit. Here's the representation of the analog signal and the 2-bit sampling rate that we have. So at the backdrop, you see the signal represented by the digital output and the signal of the original analog signal overlapping. You see some distortion. This distortion happens because we are using only 2 bits decoding, or 2 bits to represent the analog signal. So to get a better signal, quantization, if we need a better signal quantization, we can always add another bit, or maybe a 3-bit, a 4-bit, a 6-bit, up to 8-bit, 16-bit. It's up to you. So let's look at this as an example with a 3-bit. We apply a 3-bit coding. So if we use a 3-bit, if you can see here, the digital signal now is much more better following the original analog signal. So this means that whenever we increase the bit, we actually increase the accuracy of our conversion from analog to digital. Okay, when we increase the bit, we increase the conversion. Use of original analog. Okay. So now this is an example for a 10-bit processor applying 3-bit coding, better presentation. Okay, this is one of the example of a Max MCS12 ADC chip. I'm going to skip that. Okay, so to improve out the accuracy, usually we get a better sampling rate. So that means we increase the frequency of sampling rate. The higher the sampling rate frequency, the better the accuracy of the signal. Okay, so here in this graph, it represents on the left side is the sampling rate, and the right side is the resolution, the bit depth. So that means when we have a better sampling rate and a better resolution bit depth, we have much more better accuracy of changing from analog to digital. So what we need to know is that we need to have a better sampling rate. That means the rate of sample, the time of sampling, and the resolutions means the step or the representation of the analog graph in digital. The higher the bit rate, the better the resolution. Okay, so we are going to stop here and continue on our next video.